Okay, so 3.5 is called related rates. Okay, so this is where the calculus starts to come alive and we get to start using real world scenarios with calculus. Okay, so we're going to have some story problems. The piece that is the most important for you to remember when you're working with related rates is that everything is with respect to time. Okay, what does that mean? Everything is dt. dRdt, dAdt, dVdt, dxdt. We did do this last year, so this will be a review for some of you.
I still was bad at it.
I'll probably still fail.
Yeah.
Like, this is the test you got.
Can only get better, right?
This is the test I got a 30 on.
Debatable. Yes.
Okay. So the nice thing is that this book has kind of outlined a procedure for you. Okay, the first step says draw a picture. Okay, so if you can draw a picture to represent the scenario, sometimes it helps to have a visual on the idea. Okay, it helps you maybe draw a triangle, maybe whatever. Come up with the correct formula that you need. Okay. Step 2 says write what is given and what is to be found using the variables. So if we're looking for a dr, dt, a whatever. Okay, so start by writing down all the pieces that you've been given. Okay, then we're going to write an equation. Okay, so it says if the quantity is changing, it must be represented as a variable. Okay, did you hear that part? That's such a huge idea, you guys. If something is changing, it has to be represented as a variable. Okay, so that means like if I have a circle that's growing, okay, and we're just kind of maybe analyzing the area of this circle that's growing, okay, the radius would be growing at some rate. Okay, so we would have to say, okay, well then our r has got to be represented as a variable of r. We can't say the r is going to be 5, because it's not always 5, right? It's always growing. Okay, constants, something that stays the same, is going to be represented by a number. Okay, so the thing that just hits me right away is like, let's say we got this ladder, okay, and we have a ladder that's like falling down a wall. Okay, the ladder's length is a constant value, it never changes. But the height on the wall changes, so that would be represented as a variable. Okay, so we'll probably do a problem like that, I would guess. So look for secondary relationships between quantities and reduced numbers. Okay, then number 4, we're going to explicitly differentiate with respect to time. Okay, so we're just doing what we did in the last section, but now everything is with respect to time. Okay, and then we substitute our stuff back in. Sound easy?
No.
All right. So in case you didn't know, here are some geometry formulas. I hope that most all of these you already know. I assume the right triangle? Nailed it. We got a Pythagorean theorem. We have an area equation for a right triangle. Do remember that when you're doing an area of a triangle, the base and the height have to be what? The base and the height must be perpendicular. A lot of people forget that you have to have a perpendicular height. Okay? Okay, duh. We'll see. Circles. You know the area of a circle is pi r squared, and the circumference of it is 2 pi r. A sphere, we already talked about this earlier today. The volume is 4/3 pi r cubed. The area of a sphere, anybody know this one? The area of a sphere? 4 pi r squared. That's like the surface area.
Bless you.
We got a cube, we got a cone. Everybody knows the rectangular and its perimeter. So maybe a few new ones in there. So probably a good thing to write down on a cheat sheet is anything you don't know. All right, here we go. So question number 1, we ready?
Yes.
Okay, we have some given information, and it says we need to complete only the first 2 steps. Okay, so they're giving us the area equaling s squared. So by the way, what formula is the given piece? The area of a square. Okay, so this is just, we're talking about the area of a square. It says the ds dt equals 3, and the instantaneous information is 4. Okay, so let me kind of set this up for you. Jacob and Garrett, are you guys paying attention?
Yeah.
Number 4?
Yeah.
Oh. Oh. Okay. So the idea of this is we have this square. Okay, so we have a square that's growing. Okay, so the ds dt is telling us that this square is growing at a rate, or the side length is growing at a rate of 3, feet per second. Okay, what we're going to do is we're going to find the rate of change of the area when the instantaneous side is equal to 4. Does that make sense, the idea of what's happening?
Yeah, sure.
Okay, so the square is growing. We're figuring out what the rate is right when the side length happens to be 4. Okay, all right, so they gave us the information. We're kind of down at, we're down at step 3 right now. Okay, well, actually we're down at step 4 because they already gave us the equation.
Oh yeah, baby.
So we're at the part where we're just doing our differentiation. Okay, so we have a equals s squared. Can you tell me what the derivative with respect to t of a equals s squared is? Good. dA dt equals
Oh, I remember this now.
2s. And then what's the last part?
ds dt.
ds dt, because we just derived s in terms of time.
Oh. Yeah, that's what I got.
Okay? So once I have derived it, now when I plug in my given information, so they're giving me a ds dt, they're giving me an s, so now we replace the s with 4 and the ds dt with 3. Yeah, it's all right there. Okay, so 2 times 4 times 3 is 24. Okay, the one thing I don't like about this question is that it doesn't give us any units. If we were doing a dA dt, remember area is always represented as units squared. Okay, rate is always in terms of time, so per second. So it could be like feet squared per second. Okay, and I think it's really important that you understand the unit notation, because sometimes they'll just give you a measurement and you have to decide what it is. Are we talking about an area rate of change, or are we talking about a volume? Okay, so that becomes really important. Okay, let's try B. Okay, so for number 6, they rate this slightly differently. They give us an instantaneous rate of change for the x as -6. So in this case, the x is getting smaller. Okay, so negative meaning it's getting smaller. Okay, the instantaneous length of y would be 4. The equation we're going to work with is xy is equal to 4. Or 12. Sorry. Okay, and we're going to find the dy dt. Okay, so we're taking the xy equals 12 and deriving it in terms of time. So what is the derivative of xy? Which rule do I have to use? Okay, if I have two things that are being multiplied, what rule do I have to use? I got to do a product rule here. It's a firsty second plus secondy first. Okay, so my first is what? X. What is the derivative of y with respect to t? Good, dy dt. Plus second d first. What's the derivative of x with respect to time? dx dt. Good. 4? What do you mean 4?
Yeah, our 4 just didn't.
It looks like a
our 4
little
didn't show up.
carrot.
Yeah.
You know what you call?
Yeah, on our paper.
Why
Why 4 is why
it looks like a carrot.
No,
Oh. Oh yeah, okay, so use a 4 instead of a carrot, because a carrot makes no
I was
sense.
a little confused.
Okay.
my meat.
Okay, now we got to derive the 12, so we're on the other side now. What is the derivative of 12?
0.
0. Wow, that was a bad 0. All right. So at this point, I can go ahead and plug in the information that was given, and then I can isolate my dy dt, or you can start by isolating the dy dt and then plug it in. I think I'm just going to plug this stuff in and then isolate dy dt. Is that right? All right. So anybody know what my x value is? How did you get 3? Ah, good, right? So you have to use some of the given information to come up with some of the missing variables. It says that x times y is 12, so x has got to be 3, right? Very good. Dy dt, we don't know what that is. Okay, the y that's given is 4. The dx dt is given to us as -3. Okay, so we just replaced the given information, some information we had to gather. Okay, so we had to conclude that from the given information. So if the equation is x times y equals 12, and the y is 4, we can find that the x is 3. So to isolate my dy dt, can I go ahead and add the 24? Everybody's okay with me saying equals 24? Is that all right? Yeah. And then divide by 3. So what's my dy dt? Okay. Oops, dy. It's important to write your variables correctly. Dy dt is 8. Okay, so that means that the length of the y is changing at a rate of 8 units per second. Yeah. Something's. Or minute. Could be per minute, yes. Alright. Oh, yes, here we go. Alright, so in my notes here, I have this problem highlighted. So there's probably a good reason why I have it highlighted.
It's important.
It's important. You might see it again. It's important you know how to do this. Okay. So we have a windlass is used to tow a boat to a dock. Okay, so it's, imagine this rope pulling this boat in. Okay, the rope is attached to the boat at point 15 feet below the level of the windlass. Okay, so the given information is on the little triangle. If the windlass pulls the rope at a rate of 30 feet per minute. Okay, so I'm going to stop right there. And I'm going to identify the information that was just given to me. Okay, so it says, if the windlass pulls the rope at a rate of 30 feet per minute. Okay, what is that giving me?
The RDT.
Okay, so do you see my triangle? Okay, so my one leg is 15. My x is the distance between the dock and the boat. My x is the length of the, or not my x, I said z. The z is the length of the rope. Okay, so if my rope is being pulled in at a rate of 30 feet per minute, which variable is being affected? The z. So this is a rate, so it's a dz dt. So I'm going to say dz dt. Now, is it a positive value or a negative value? Is the rope getting bigger or shorter?
Shorter.
So what kind of value represents shorter? Negative. Good. Okay. Continuing on, at what rate is the boat approaching the dock? Okay, I'm going to stop.
X.
What is the question? They're asking us to find sorry. We are trying to find dx dt. That is the question. When there is a 25 feet of rope out. So when the z is 25. Is everybody okay with the given information?
I remember doing this last year.
I like this so
Good.
much.
Question mark.
Question mark. Okay, so if we're talking about a right triangle and we're analyzing the lengths of those sides, what formula do you think that we're going to use?
Pythagorean.
Pythagorean's theorem. Okay, so set up Pythagorean's theorem for me. Okay, so set up Pythagorean's theorem. So it's going to be x squared plus 15 squared is equal to z squared. Now, is everybody okay with when I use variables and when I'm using a constant? Why am I using 15 instead of some variable there?
Because 15 is how tall the wind blasting is.
Right, it never changes. It's always 15 feet above the ground. Okay, so we can represent it with a constant. Okay, so now we're going to derive this in terms of t so that we can analyze the rates of change. So starting with x squared, what is the derivative of x squared? 2x dx dt. What is the derivative of 15 squared? Derivative of a constant? 0. The derivative of z squared? 2z dz dt. Okay, now what do I do? Plug in the values. Okay, so, I don't have an x. How do I find the x? I'm missing an x. Okay, so I'm going to have to do a little bit of sidestepping here to find the value of x. So remember that the instantaneous length of the rope is 25. Okay, so I can find the instantaneous x value when the rope is 25 by doing a quick Pythagorean theorem. Okay, so if I do x squared plus 15 squared equals 25 squared, can somebody tell me what my x value would be?
Let's look.
20. Nice. Okay, so now I can take that 20 and plug it into my green equation with my rate stuff. So I have 20 dx dt, that's what we're trying to figure out, the rate of change of that, the dock getting closer. I'm just going to get rid of the 0 because it's just a 0. The z is 25, the dz dt is negative 30. Okay, so now we're just crunching numbers. I've got 40 dx dt is equal to 50 times, so negative 150. So divide by 40. What's negative 50 divided by 40? I don't think that comes out nice. Oh, I'm missing a 0 too, by the way. I missed a 0 in there. So what'd you say? 37. So negative 37.5. Sorry, that was my bad. 37, yeah, because I missed a 0. Now, I have to label this. Okay, so we're talking about a rate of change of the x. We're talking about a distance that is changing. Okay, we're looking back up and saying feet per minute. Nice, okay, good eye. Okay, so it is very important that you label these units correctly. That's one of the pieces that I will be looking for on the test. How do you do on that one?
I think I won.
Good? You won? Nailed it? Okay. All right, let's do this last one. Okay. So this question is, this is like a question that's happening right down the road. They're filling a pile with gravel. Okay, so we have this falling gravel on a conical pile. Does anybody know what a conical pile is? It is a cone. That's a cool word for conical, like cone-ish shape. So we got a cone, and it has a rate of 10 feet cubed per minute. So I'm going to stop right there and talk about what was just given to me. They gave me a rate, okay, it says rate, and it says 10 feet cubed per minute.
That's not a big minute.
So what did they just give me? They gave me a volume. How do you know it's a volume? It's cubed. It says feet cubed. Okay, so that's how I know that they're giving me a volume. So we have a dV dt, okay, and is the pile growing bigger or is the pile getting smaller? Bigger, so we know it's a positive rate. Okay. At all times, the radius of the cone is twice the height of the cone. So how could I say that? The radius is twice the height, yes. The radius is twice the height. That's a new one. Okay. So find the rate of change of the height of the pile when the radius of the pile is 6. Okay, so find, what are we trying to find? Good, we're looking for the dH dt. That's the question. And when the r is equal to 6. Okay. So,
this is challenging.
now the next step is figuring out what formula we're going to use.
Cone.
Okay, we're working with a cone. Okay, what specifically? What piece of the cone? We're talking about the volume of a cone. There you go. So, what is the equation for the volume of a cone?
1/3 pi r squared h.
One. Wow, that was very nice. Pi. Oops, I forgot my r. Pi r squared h.
That's just hours of dedication.
Okay. Okay. So, before I start deriving this, does everybody see how at this point in time I have two variables that are in my equation?
Yeah.
Two variables. So I have technically an equation of volume that's in terms of r and h right now. Okay, so what I need to find is an equation of volume that's only in terms of h, because I'm trying to find a dH dt. I don't want a dr dt. We don't have any information about dr dt's. Okay, so I need to eliminate my r. How am I going to replace the r value?
We're 6 into that.
2h.
Okay, well yeah, it says it right here, right?
Yeah.
Because my r is equivalent to 2 h's, so all I have to do is replace my r with 2 h's. Okay?
I know not to use the 6.
We don't use that till after we derive.
Alright.
Okay? Alright, now I am going to simplify this before I start deriving this. So, I have a 2 squared. What is 2 squared? 4. So I'm going to take the 4 and I'm going to throw it out front. Make sure you're watching this, because if you're not paying attention, you're going to be like, where the heck did that just come from? Okay, 2 squared is 4. I have a 4 times 1/3. What's 4 times 1/3? 4/3. So I have 4/3 pi, and how many h's? Cubed. Right, because we have h squared times h. What's that?
A lot.
It looks familiar, doesn't it?
It looks like
I know. It's a good eye.
How do you do that?
How did I do that? I just simplified.
Because she has a degree.
Well, how did you get the 4 to multiply by the 9?
Did you not say I just said that?
No, I was trying to write the rest down. You're going
We're
fast.
following you.
I was still.
Where did the 4 come
Still
from?
lost.
I'm just slow.
Okay. 2 squared. What's 2 squared?
4.
What's 4 times 1/3?
Okay.
4/3. Okay, so I'm going to drive this up over here. Okay, so the derivative, remember we're deriving in terms of time. Derivative of v is dv dt. The derivative of 4/3 pi h cubed is 4 pi h squared dH dt. Good. Everybody okay with the derivative?
Wait, so why don't you use a problem?
You're going.
There's only one variable.
But I
If I would have kept it back here, like if I would have had the information about a dr dt back here, I could have done a product rule and then a first and second. So it's fair to do that, but I would have gotten to a place where I couldn't have done anything. Okay, now what do I do? Plug stuff in now.
Yeah.
Okay, so what is my dv/dt? 10.
Oh,
We're given 4 pi dh. Okay, so think about this for a second. If I have an h and it says, remember this little piece of information? Okay, my r is twice my height. So what is my r, or my h? My h will be 3 because it's twice as big. Well, the r is twice as big. And then dh dt is what we're looking for. Okay, so we need a little bit of calculating. Let's see, we've got 3 squared is 9, 9 times 4 is 36, 36 pi dt, oops, I wrote that wrong again, dh dt, and now divide by 36 pi. So, anybody got a calculator and can divide 10 by 36 pi? Make sure your 36 pi is grouped together.
0.87.
0.0, what'd you say?
0.87.
I have a different number. Make sure you have, when you do 10 divided by 3 pi has to be grouped. So in parentheses, 3 pi. Or yeah, sorry, 36 pi. Yeah, that's what I got. Does that make sense, Garrett? Because if you just do 10 divided by 36 pi, it's going to divide only by 36 and multiply by pi instead of dividing it, because it's order of operations. All right, what's my units? Since it's change rate of height. What'd you say? Feet per minute. Is it cubed though? Height is just the length, so not cubed. Only if we were talking about a volume would it be cubed.
Wait, so when would you use squared?
If you're working with an area, yeah.
But this
Yeah.
is volume.
This is volume. Well, dh is a length, so